Quite well. How are you?
Okay, how are you?
Oh,
Hey, Moshe.
Hey, guys.
How's it going?
Great.
All is well. Oh, got some more people. Dum, 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 ba-da-dum, dum, dum. Okay, okay.
Matt, can you hear me?
Yeah, I can hear you.
Okay, thanks.
Nice. All right, there we go. Do 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 do. Moshe,
Yeah.
unfortunately, I'm not going to be able to make it to your meeting tomorrow, but if I hope to see it if you record it. Unfortunately, I have some plans in the afternoon.
I will definitely try to record it and post it.
That's awesome.
I will definitely make an effort, even though I'm very poor at editing video. I guess I don't have good editing software, but I will definitely do my best.
Hello.
I'll secretly record it
Oh, great. Nice.
for the KGB.
Mm-hmm.
And you.
I think that's a great idea.
I started watching
It's going to keep them busy. It's a good way of wasting their time.
They're not called the KGB anymore. I forget their name, so I'll have to.
GRU.
Find them.
GRU.
FSB.
GRU. Okay.
GRU.
I started watching those quantum field theory lectures by Sidney Coleman, and at the beginning of it, he makes a joke where he's like, "You may have noticed there's these cameras recording this lecture. It's for a secret CIA project."
And it's not a joke anymore.
Crap.
Everything is recorded.
Yeah, well, voluntarily too.
Every landline call and every digital call is recorded by the teleconference.
And every step you take is recorded by, 50,000 cameras in Manhattan.
The NSA is listening to every single online communication. There's drones. There's ability from 2 to 3 blocks away to listen to conversations in your home. There's absolutely the notion that we have a Bill of Rights or civil liberties any longer is utter nonsense.
Oh my God! I'm gonna
Guys,
have to.
I think you just managed to resolve the information paradox.
I'm gonna have to disavow every terrible thing I've said about Victor. I didn't mean it.
I feel like there's safety in numbers. I mean, that's the thing. So they're recording everything. That's a lot of data to go through. I mean, it becomes a kind of a needle in the haystack problem. It's actually, I feel like it's easier when you're just spying on, a couple 100,000 people, because then you can.
No, but they're just listening for keywords, for
Yeah, well,
instance,
that's the problem, right? It kind of becomes deep.
It's not the CIA you have to worry about. It's Mark Zuckerberg who you have to worry about.
Yeah, well, who's on Facebook anyway? At this point. So today, a couple things. I thought, before we get into second quantization, just a couple more things about coherent states. I thought might be kind of interesting to talk about briefly. Because I just think this coherent state thing is really cool.
Matthew, can you make it a little bit bigger? I have difficulties reading it.
Yeah, make it big.
That's much better. Thank you. Fantastic.
Yeah, totally.
Great.
yes, much better, much better.
Oh yeah, Marty's not here. I was going to point out to him that, he asked last time about the relationship between coherent states and lasers, and I sort of waffled a little bit on it. But yeah, it's true that coherent states describe lasers or whatever. Like if that, I guess it's like if the oscillator represents like a one frequency mode of the quantum field, then the laser is going to be in like a coherent state.
How about this? The 3D films are made possible because of the spin 1 or spin -1 spin of photons. That is why we are able to watch 3D movies.
How do you mean?
You explain it.
But you mean
it was just something that I saw in passing. You have two lenses on the glasses that you're wearing in the theater, and one of them screens out the spin 1 particles, and the other spins out the spin -1
right, the polarization.
And then and then your eyes, your brain links together the image from the left and right eye and forms a 3D image.
At a little later on, yeah, we're going to talk about polarization. And actually, for now, it's a funny thing. Like there's this, apparently, we might be able to see polarization. Like I can't confirm this. There's this Wikipedia article here. Heidegger's brush. Many people are able to perceive the polarization of light. Yeah, I mean, if you look at a blue sky or like a computer screen in a certain way, you can kind of perceive the axis of polarization or something, as this sort of blue versus yellow thing. I don't know. I can't. I spent a long time trying to see this, and I don't know if I was entirely successful.
I think it's just cataracts.
Yeah.
And half of the people here have them. So,
but there was an experiment that they did, where apparently they were successful. It's easier to see when they were like basically like shooting photons into people's eyes, and the polarization was sort of constantly like rotating, and then they're like asking people questions about it, and people were able to guess the polarization greater than chance. There's like an interesting study. Kind of cool. I don't know if we use it for anything, but yeah, I mean polarization, it's real. It's a real thing. Okay.
What's wrong with Polaroid lenses?
Polaroid, yeah. Well, that's what we.
That does the same thing.
Yeah, at one point I bought online, a whole bunch of little, polarization filters. Because it's funny, you do the thing where you stick the, you got like a vertically oriented one, you got a horizontally oriented one, and then it blocks all the light. But if you put a 45-degree oriented one in the middle, then some goes through, for basically quantum kind of reasons. It's something like, goes through the horizontal one. So if it goes through the horizontal one, it ends up horizontal. And then if it goes through the vertical one, like it'll never do that because horizontal will never go through vertical. But if you send it through a 45-degree first, it'll, end up going through the horizontal one 50% of the time. Anyway, it's fun to see.
Here is to always be the naysayer. Scientific American says that for the spin to actually exist as a physical property of the particles, of the subatomic particles or atoms, the spin would, the particles would have to be spinning faster than the speed of light.
Yeah, so well, I mean, yeah, it's like if you're trying to fit it into a classical picture, like the electron's like a tiny little sphere or something that's spinning around, then that, you know, apparently doesn't make much sense.
But this is part, it just as part of the discussion, this is why I posted the image that was taken, which used electrons to image photons. And what you see is actually, what you see is what look to be wave packets, but one of the reasons to be somewhat skeptical even of what you are seeing is that it is described in this by the institute in Lausanne that took the image as a standing wave. And so the photons that are being imaged were traveling both in a direction to the left and a direction to the right along the same nanowire. And it was that standing wave of the two waves interfering with one another, different kind of interference, that created the effect of a standing wave, and which is the first image that we ever have made of this. It's described as the first image we've ever made of both the particle and wave nature of matter. When I look at it, if you looked at it, and I hope you did,
I did.
I don't see a particle anywhere. What I see is a three-dimensional wave packet of some kind. If I want to stretch my imagination, I could see, for the Bohmians here, I could see nodes near the top of this parabolic-like shape to the wave, which could be the particle that is riding the wave. But what I see essentially in this image is this standing wave. So it's once again, there's the issue of the observer and measurement, and we're altering the nature of nature when we try to image it. But I see wave packets that are three-dimensional, that are somewhat parabolic. I see no particles. Yeah.
Victor, what you're saying is in complete conformance with quantum field theory. Everything is a wave packet. Every particle is a wave packet. There's no such thing as a point particle. And both Bohm and Copenhagen theories are incomplete theories because they are non-relativistic. And we live in a relative. My only contention is that Bohm better describes what's going on. But you're right. There's no such thing as a particle. As a point particle, what we call a particle is an excitation of a field. It's a wave packet, excitation of a field. That's what quantum field theory tells us.
Well, the reason, why am I making this point specifically here? And this is, I sent it out because we were discussing spin, and it's to deny the analogy, both linguistic and mathematical, to spin as angular momentum, as axial angular momentum of objects, softballs, the moon, the sun, whatever. This is the analogy is not there. So we're using the word spin linguistically, and we're using the mathematics of angular momentum as an analogy for what Stern-Gerlach saw, which is the particles being affected by a magnetic field. Okay, so this is the origin of the analogy, but the analogy is highly imperfect. It is literally inadequate because it's not equal to the phenomena. So it is, I just think we have to, as we have the entire discussion, keep that epistemological certainty in mind at every point.
I'm there with you. I mean, I think also, it's like, well, to say something about the imaging the photons with the electrons. I read the paper a little bit, like I didn't quite work through it. But, I just wanted to say that, there's no contradiction in being able to, to some extent simultaneously image where something is and how fast it's moving. It's just that, like, you know, to the extent that, you know, you measure the position with a certain accuracy, there's uncertainty in the momentum. But that doesn't mean that you can't have some kind of compromise between them and get a little bit of, you know, both kinds of information at the same time.
Is there a branch of mathematics in quantum mechanics, or a kind of like peripheral branch which is attempting to do that?
Yeah, I mean, you know, yeah, I mean, you can, people try to make all sorts of measurements. You know, I mean, it's like people aren't just sitting around just trying to like measure just position or just momentum. I mean, as far as spin's concerned, you know, I mean, I agree with you completely that it's like there's an extent to which spin is like analogous to angular momentum, and there's extents to which it's not. I mean, our, you know, cool picture of the points on the sphere and stuff, I think, you know, shows how far we can push the analogy to something spinning, you know.
Can I say something?
But,
Spin is more than just an analogy to orbital angular momentum. In fact, in every experiment, spin is arithmetically added to orbital angular momentum. They are one and the same phenomenon.
Yeah.
It's not just an analogy. So,
no, it's
so yeah, spin is an unfortunate terminology. Yeah, the electron is not spinning on its axis because, as we pointed out, it would have to be spinning faster than the speed of light. But nevertheless, it is one and the same phenomenon as orbital angular momentum. They are always added in any experiment you do.
Axial angular momentum.
What do you mean by axial angular momentum?
Meaning that it's spinning on its axis as opposed to
it's not
orbiting.
Really. It's not really. That's an analogy to classical physics. But the thing is, what I'm saying is orbital angular momentum of an electron and its spin are always arithmetically added. They are one and the same phenomenon.
What do you mean by spinning
spin
on
is
its
an unfortunate
axis?
terminology.
What is the axis of an electron?
yeah, well, you know, I mean, if you use my sphere thing, then you can figure it out by just adding up the directions all the stars are in, and then you get the average axis that you could reconstruct that the thing is spinning around over many experiments.
It can have an axis, but
okay, if it spins, it always spins around an axis.
no, but
There's
it's not
no other
spinning.
spinning except spinning around an axis. But the electron, as far as I know, does not have some sort of an inherent axis.
Sure.
As far as it spins, yes, if it spins around an axis.
No, but it's not
This
spinning.
is a tautology.
It's not spinning, Moshe. Spin is an unfortunate term that's been applied to it. It is not actually spinning.
Well, later on we'll see. So, I mean, one way of interpreting, you know, the little spinner, right, is that you have these two complex numbers, and, you know, you can take their ratio and stereographically project from the plane to the sphere, and or take the expectation values of the Pauli matrices, and you get this axis, you know, this sort of average spin axis. But there's more information than just the axis. There's the overall phase of the spinner. And you can view that phase as like how much it's sort of turned around that axis. And later on, we'll see when you can sort of also interpret a spinner in terms of polarization. And there, you know, you can interpret the spinner is both the specification of a little ellipse, like the electron's like corkscrewing around some ellipse, and the phase tells you like how far it's like gone around in the ellipse.
But okay. This is a 3D temporal image of the combination of orbital angular momentum and axial angular momentum, which are classical ideas applied to the quantum realm. And it's just as much, when you talk about a spinner in that sense, it's just as much an abstraction of what is occurring in nature as the wave function.
Yes. Well, what I'm saying is, so spinners, what's cool about spinners is they kind of have a foot in the classical and in the quantum world. In other words, I could use a spinner to like represent a classical spinning object, because the spinner represents both a 3D like direction and also like an amount to be turned around that direction. Furthermore, a spinner can also represent like a classical photons polarization or whatever. In other words, it specifies both an ellipse and like what point in the phase you are as you're like going around the ellipse. But then we also know that we can sort of interpret like a normalized spinner as a qubit. And therefore you can also interpret it as like a quantum thing. And the idea there being, it's like, then, you know, you have to consider like actually like measuring it. And then so that's what's cool about spinners, basically. Like you're using the same mathematical object to represent like both kind of like the classical thing and the quantum thing. And you just sort of, the difference is kind of like in how you interact with them. In the former case, it's just sort of like, just look at it. In the latter case, you got to use these operators, like measure things, and of course, measure.
And also, bear in mind that because we use the same math to describe two different phenomena, you know, doesn't make the two equivalent physically.
That's true, but I think that
here would
especially
be
because people often get a little bit kind of crazy about, you know, like what are the, you know, these weird complex numbers and these, you know, I think the spinner formalism like makes the analogy between the quantum system and the classical system like as close as possible.
Here's the problem with the analogy. It would be the equivalent of saying, okay, there is an analogy to be made between you know, the point particle and say the Earth. Okay, and because the electron, for instance, will leap from one orbital to another instantaneously, or more or less instantaneously, and both of them spin, the Earth also can leap instantaneously into another orbital around the Earth. This is the equivalent of the analogy that we're making linguistically and as well as mathematically to spin.
There's so many different ways. I mean, in a way, it's like there's so many different ways the Earth is spinning that, I mean, would you even notice if it jumped like a little bit?
Well, the Earth, that's the issue too. In the classical realm, the spin can transition through various speeds and various phases. When you talk about spin in the quantum realm, it's always integer spin or half integer spin. And so that especially completely fractures the analogy.
It's like when you consider a classical spinning object like emerging from the quantum picture, it's like, you know, its spin is huge, you know? Like you can take like all the particles that make up the Earth and like add up all their spins, and like that's the quantum spin of the Earth. But if you were to send an Earth through a Stern-Gerlach, I mean, it would split into just so fucking many beams that it's like effectively continuous. And moreover, unlike a little spin that's isolated that you're just like sending through a Stern-Gerlach, the Earth is also, you know, constantly bombarded with shit and interacting. And so there's just like a huge amount of decoherence and stuff. But in principle, you know, I mean, I completely agree with what you're saying, which is that, you know, you gotta kind of be careful about like using your classical intuitions. At the same time, like all this stuff at the end of the day adds up to classical reality. So if it can't, you know, there's gotta be, you know, for it to really be a good theory, like there's gotta be this sort of explanation of how you get from the quantum to the classical.
That step, I don't know. I think maybe we have a perfect or reasonably adequate or reasonably adequate mathematical analogy, but that's, to me, is the end of it. Maybe it's even a perfect analogy, but we cannot explain why it is, because precisely for what I said. You've got, integer spin, half integer spin. And the Earth, for instance, the spin of the Earth has been slowing down.
Well, the more
because of the tidal forces of the moon.
True.
And because of the shift in the position of the moon.
Well, again, I mean, like you keep saying, I mean, you should distinguish between, the Earth is spinning, right? But I mean, the closer analogy to like the spin of the Earth would be the Earth's magnetic field, right? Like the magnetic poles of the Earth.
Right.
Look, the reason the analogy breaks down is that on the quantum level, both spin and orbital angular momentum are electromagnetic phenomena, whereas the spin of the Earth is a gravitational phenomenon or a mechanical phenomenon.
Well, that's what I was saying. It's
not the same thing.
The magnetic, field of the Earth, and then so I mean, that's more like the spin, and then the actual fact that like the Earth as a whole is like rotating. That's more like the orbital angular momentum.
But it's only an analogy. I mean, Victor is right. It's the Earth can rotate without there being an electromagnetic field. Yeah, there's a magnetic field, but it's another phenomenon.
Because of the iron core, iron nickel
Yeah,
core.
right. But that has nothing to do with the Earth spinning on its axis or revolving around the sun.
Yeah, well, there's a funny story about, someday we're going to have to talk about how, there's a fascinating story in the history of science about, the old quantum theory, right? Pre-1927, and how, like initially people were trying to analogize like the atoms to like, planets that are spinning, and the electrons like little moons, like orbiting the planet and stuff. And, the crazy thing is that like that analogy really worked for the hydrogen atom. It doesn't in general work like but the fact that the analogy worked in that case is sort of how Bohr was able to come up with a lot of the early results, even before the theory was, fully worked out.
Well, that was one of the reasons, that was the reason that I posted the other image. And I was hoping that instead of being just in the mathematical realm, we would actually attempt to have some empirical understanding, which I don't think is possible, of what is occurring at the quantum realm. Not at this point, not based upon the how finely tuned our instruments are at this point, how well they can observe. But I posted what is it's based upon the wave function of the electrons in a hydrogen atom based upon their energy levels. And what it strikes me about this, as opposed to the notion of randomness at the quantum level, is the precise geometries that are based upon the energy levels. And you get a mix of concentricity, radial symmetry, and bilateral symmetry. With the concentricity, you get rings and Horaces. With the radial symmetry, you get radial teardrops or cloverleafs. And with bilateral, you get bilateral crescents or lens shapes. So you get this.
It is very cool. Yeah, but there's no contradiction, right? Because think about even just at a classical level. You're thinking about, the vibrating string, or you do the experiment where you put some sand on a piece of paper that's on a speaker and you play some sound, or you're thinking about the way that like some water droplet is like vibrating. That's just completely classical. And, you solve the partial differential equations for those systems. And what you get is like an infinite number of like geometrically beautiful solutions that in the case of the vibrating string, you get a bunch of standing waves, or if you're like solving for the vibrating drum head, you get these cool geometrical patterns or whatever. You look at, some 3D thing that's vibrating, and it's, there's all these different modes that it can be vibrating in. And then what you do is you describe any way that the string, the membrane, the droplet or whatever, any way that it's vibrating as a sum, as a linear superposition of those basic movements. And those basic movements are like very aesthetically pleasing. They all have this like very kind of like, like very like clean, like geometric thing. But those are just like the fundamental modes, the fundamental vibrational modes of the thing. And then, what you do is like, you say like, all right, I want my system to like start off in like this initial condition. And in order to like encode that in, you kind of expand it like in a Fourier series, like you expand that function in the basis formed by those fundamental vibrational modes. So that's already a thing in classical physics. The difference in quantum physics is just that, the thing that's vibrating is a probability wave. And there's this whole thing about measurement. You know what I mean? So like the fact that those things are so geometrically beautiful, you can see that shit in classical physics too. It's the same idea. It's the question of, what's vibrating in the quantum case. And, it's these wave functions, not a string.
So Matt, let me ask you something. In quantum field theory, in second quantization, is that a probability of something vibrating, or is it an actual field excitation?
Yeah, well, by the end of today, we're gonna talk about second quantization. So yeah, like let's like save that for a second.
But just the last thing about those images of geometric beauty, right? Of concentricity, radial symmetry, rotational, and bilateral symmetry, which you see.
Yeah, like
that if it weren't for that,
sorry.
If it weren't for the degree of geometric definition that you see there would be no periodic table. There would be no crystal structure.
Oh, yeah.
There would be no neutron stars. So this is my point about the use of the word random to describe a process which is, we haven't reduced it yet to all of its components, and so we use the word random to describe it. What we're describing is complexity, and what we see in those shapes and those geometric perfections is an ordered disorder or a disordered order, and so it's chaos in the new sense of chaos, and it is not. It's complexity. It is not randomness, and if it weren't for that underlying order at every scale, then, like I say, the periodic table would not be there.
Yeah, I feel what you're saying. I think the thing that, the thing that makes the difference here is that, see, like, look, what's happening here is there's a speaker underneath this plate, and the guy's poured some sand or some salt, and is playing some tones. And you see that, there's these like vibratory modes, and so you get these beautiful geometric patterns. And in general, like in classical physics, like I'm saying, you can, decompose like how something is vibrating into these different vibratory modes, whether it's a one-dimensional or two-dimensional or three-dimensional thing. The difference when you get to the quantum thing is that basically like the measurement postulate says that when you go to measure the system, it collapses into one of those vibrational modes. And that's not something that happens in classical physics. You see what I'm saying? The randomness has nothing to do with the, geometrical patterns or geometrical structure. The randomness has to do with when you measure it, like weirdly, you like get one of the basis states like at random. So,
but that's not a random. That's not a randomness of. That's not a randomness in nature. That is an effect of measurement upon nature. That has nothing to do with the nature of nature.
I
Oh,
I
again,
agree with Victor.
you can interpret it in different ways. It's just like, I mean, that's, however, whether it's, you accept a Bohmian picture and it's like the reason you get like some eigenstate is because of whatever, like, you're modeling it almost in a classical way, the intervention of the measurement apparatus on the situation. Either way, it's like, in classical physics, it's perfectly possible for something, when you like look at it or measure it, to be in like a superposition of these vibrational modes. But that, the thing that quantum mechanics sort of adds to this picture is that measurement in some way seems to select one of those vibrational modes. Now, however that happens, if it's a fundamental indeterminism about the world, or if it's some Bohmian thing, I don't know. I mean, I'm not going to be.
Again,
that is the difference. You see, there's like this thing, this added extra bit that you consider in quantum physics.
A divine being, and I don't believe in divine beings. A divine being outside of nature that can observe nature without intervening in nature, that can measure it without a measuring device, would not be having the effect on the quantum system that the measurement is having. Then you would know the condition of things that this too is a thought experiment, it's an abstraction, just as the wave function is an abstraction. You just have to step outside of the declarations that are being made, philosophical declarations that are being made on the basis of the behavior in the quantum realm. You have to step outside of it and recognize that this is your flaw as a human being that is limited in scope, limited in perception, that affects things with observation and measurement. That's all. That's the only thing that you are looking at. You're not looking at nature when you do this.
Well,
we are confusing randomness with a statistical distribution. In theory, you could measure all these things if we knew how to do it, and if the measurement did not affect if the active measurement did not affect the value of the measurement, which on the quantum level it always does. But what I wanted to say, Victor was commenting on the beauty of the solution of the hydrogen atom. The reason it's so beautiful is because of the assumption that we make of spherical symmetry, which turns out to be pretty close to accurate for a hydrogen atom, which is the only atom for which we can exactly solve the Schrodinger equation. For any heavier atom, there's no exact solution. So the beauty disappears.
Yeah. I mean, and in general, we as humans, we love symmetry. Victor, your argument just now reminded me of this. This somehow came up on my Twitter the other day. There's a famous little paragraph story by Borges, which perhaps you know about.
I absolutely love Borges, and this is from Dream Tigers. So I read it, but probably 40 years ago.
So he's like, I close my eyes and see a flock of birds. The vision lasts a second or perhaps less. I don't know how many birds I saw. Were they a definite or an indefinite number? This problem involves the question of the existence of God. If God exists, the number is definite because how many birds I saw is known to God. If God does not exist, the number is indefinite because nobody was able to take count. In this case, I saw fewer than 10 birds, let's say, and more than one. But I did not see 9, 8, 7, 6, 5, 4, 3, or 2 birds. I saw a number between 10 and 1, but not 9, 8, 7, 6, 5, etc. That number, the whole number is inconceivable. Ergo, God exists.
Look, I've got Jesus and Mohammed on a conference call.
Matthew, did you just come up with the proof that God is a bird? I'm not sure I followed the argument.
It's called the Holy Spirit.
I've got Jesus and Mohammed on a conference call. They said this is all BS.
And it's also the plumed serpent. Okay, Quetzalcoatl.
Okay, well, so let's turn to talk a little math over here. So this is a cool thing.
Matthew, as you
Okay.
start with it, please go into what you take to be the reason for picking out this particular state, what you call a coherent state.
Ah.
What is special about this sum?
Well, like we talked about last time, coherent state represents a kind of little Gaussian wave function, and it represents as a quantum system of, say, an harmonic oscillator, the best compromise you can get between having a definite position and a definite momentum. Like we saw last time, it provides, all of the coherent states provide a kind of over-complete basis for the states of the oscillator. They are eigenstates of the annihilation operator. And so that's kind of interesting. You see here, it's a sum over like all possible photon numbers. So, about to make a point about that. There's an interesting connection to
Matthew, I didn't get what you just said. All possible what?
Photon numbers, or sorry, just
Photon,
I shouldn't say photon numbers. N is the energy levels of the oscillator. If this was
Andrea, you're breaking up or something. Maybe you're moving away from your microphone because your sound is breaking up.
Andre, you still in Vermont?
There we go.
Vermont has been known to have this problem.
I think we've lost him. I think we heard ourselves losing him.
I think he slipped into New Hampshire.
I am here in New York.
Oh, okay.
So N here is, so this is, we're talking about a harmonic oscillator, and N are the different number states. So, this is like an infinite sum over all of the number states. So you can see there's a sort of intimate connection to the exponential function. Now I'm going to make a point here about its connection to the Poisson distribution. And this is kind of cool. Like, I highly recommend this book. This guy, Jean-Pierre Gazeau, wrote this fucking great book called Coherent States in Quantum Physics. And it goes into the sort of philosophy of it, gives tons of examples, and a lot of what I've been saying about coherent states comes from this book. And one of the things he emphasizes these sort of interesting connections between coherent states and probability distributions, which are familiar from statistics, and how like in some ways you can view these coherent states as being kind of like related to maybe this is an analogy like the square roots or like complexified versions of familiar probability distributions. So we'll see this in two cases here. The Poisson distribution having to do with quantum harmonic oscillator coherent states, and the binomial distribution, which relates to the spin coherent states.
Can I ask a question? Why are we going to binomial or Poisson when you already have a Gaussian distribution, and in the limit, they both devolve into a Gaussian distribution? Well, this seems to have the format of a Gaussian distribution.
Yeah, so so I mean, well, ironically, it's the spin case that follows the binomial, or a binomial distribution, same as a Gaussian distribution, right?
Right. So but even a Poisson, for a large n, becomes Gaussian. So do most distributions.
Well, so you'll see the specific claim I'm making here. So here we have the expression that we derived last week for the coherent state of the oscillator. Now we can work out this little inner product. In other words, this is the amplitude for this like coherent state, which as we know is associated with this little complex number z. What's the amplitude that this guy is in the nth number state? So, you know, we can just like substitute this expression into this little inner product. And I changed the summation to be over m, you know, just to not conflict with this n over here. You know, this is just like a scalar, so we can like move that to the outside of the bracket. We get this, but we know that like n on m is just 1 for, you know, n equals m and 0 otherwise. So that's just like a little delta. And we end up getting this, e to the negative blippity blip, z to the n over square root of n bang. And so that's the amplitude. But, you know, what about the probability? So, you know, you just multiply it by its conjugate and you get this, e to the negative absolute value squared of n, absolute value squared of, of z, then absolute value of z squared to the n over n bang. Okay, okay. Working out the expectation value of the number operator on the coherent state, you can, you know, make this bracket. We know that n is just a dagger times a. We also know that the coherent states are eigenstates of the annihilation operator with eigenvalue z. And adjointly, that, you know, when we act with a dagger on the bra version of z, it's just like multiplying by z conjugate. So therefore, actually, the expectation value of the number operator on one of these spin coherent states is just the absolute value of z squared. Knowing that, and seeing that this quantity here, absolute value of z squared, appears in this expression, we could alternatively write this as e to the negative expectation value of n times the expectation value of n, you know, the number operator, to the n over n bang, where I've just conveniently written this as that. Now, you know, recall the Poisson distribution, which gives the probability that a given number of events will occur in a fixed interval, given some constant rate of events, and the fact that the events occur independently of each other.
But given that this is the Poisson distribution, does the fish distribution in any way conflict with the bird distribution?
Yeah, is there a Loiseau distribution?
Sorry.
The avion distribution, the bird distribution.
I think that's airplane distribution. So this is the expression for the Poisson distribution. The probability that you get n events is e to the negative lambda to the n over n bang, where n is the number of times the event occurs and lambda is the expectation value. In other words, the average number of events per interval. But hey, look at that. Replace lambda with this expectation value of z on n, which remember is just absolute value of z squared. And you realize that this is just the same thing. In other words, the probability of detecting n quanta in the coherent state z is given by the Poisson distribution with lambda equals absolute value of z squared. It's almost like by specifying a harmonic oscillator coherent state, we're in some sense working with the square root of the Poisson distribution. So that's kind of cool. You can do a similar thing with the spin coherent states. So just brief reminder, because it's like been a couple, you know, weeks or whatever since we talked about this. You know, here's our basic commutation relations for the XYZ operators. We can define the total spin squared operator. When we work in the JM representation of spin, we're looking at states that are simultaneous eigenstates of the total spin squared and usually the Z operator. And, you know, the action of sigma squared is just that on a JM state, and the action of sigma Z on a JM state is just that. We can define spin raising and lowering operators as linear combinations of X and Y. You can look at their action on the states. You see they just, up to this little factor here, they just raise and lower the M value. We note that, you know, if you act with spin raising on the highest weight state, kills it. If you act with the lowering operator on the lowest weight state, kills it. And, you know, you can obtain any of the JM states by, you know, repeatedly raising or lowering the, you know, the top or the bottom state. Okay. Now, you know, what I'm about to say here is I'm going to, you know, sort of talk about spin and the spin coherent states in a slightly different form than we discussed originally. Before we were using, you know, complex numbers and stuff like that. I'm going to use a slightly different form because it makes something more clear. And, you know, if you're, again, interested in this, I'm following this book by Gazeau. So we can define the basis states of, oh, it says oscillator. Oh, I should say. We define the basis states of the spin as functions on the sphere, which are orthonormal with respect to this measure. Now here, theta is the polar angle between 0 and pi, and phi is the azimuthal angle between 0 and 2 pi. To wit, that's theta, that's phi. You know, people differ on this, right? Like a lot of people will call theta the azimuthal angle and like whatever. So just clarifying here what we're dealing with here. You know, this is like the North Pole. So, you know, theta has to do with, you know, this direction, and phi.
Your volume just went way up.
Oh, hello. Can you hear me? So it turns out that we can represent a JM state, one of the basis states of the spin, as this function phi, which is a function of theta and phi, and labeled by a J and an M. And it gives you this expression. And as I say, you know, this set of JM states is going to be orthonormal with respect to this measure. So if you take, you know, two different of these states and integrate them against each other with a little sine theta, it's going to be 0. Okay. So, you know, we have, as before, you know, this sort of binomial coefficient. And, you know, it was just written in a different form than we saw before. You got this little cosine, you got this little sine, little exponential term there. One thing that this makes manifest is like, you know, it kind of, the expression for the coherent state is kind of beautiful, right? So if this is an expression for the JM state, we can define the coherent states like this. So the coherent states are parameterized by some theta and phi. We sum over all of the different M values, and we get this expression. And as you know, we said before, these coherent states provide a complete resolution of the identity. So now let's do the same trick we did before above with the coherent state of the oscillator. Let's look at the amplitude that some coherent state, theta phi, is in some JM state. So we take the inner product to get that, and then take the, get the probability, and you get that. Okay. So now recall the binomial distribution. You have n trials, and there's a probability p of success and a probability 1 minus p of failure in each trial. The question is like, what is the probability of getting k successes? So here's the expression for that probability. And you already can see, you're like, oh, looking kind of similar, right? Now, why is this the right answer for the binomial distribution? To quote Wikipedia, I just thought I decided it's a very lucid explanation rather than put it in my own words. K successes occur with probability p to the k. N minus k failures occur with probability 1 minus p and to the n minus k. However, the k successes can occur anywhere among the n trials, and there are n choose k different ways of distributing the k successes in a sequence of n trials. So suppose we have n equals 2j trials. The probability of winning is cosine squared theta over 2. And the probability of losing is just 1 minus that, which, because we know cosine squared plus sine squared equals 1 is just sine squared theta over 2. And let's say we're interested in the probability of winning K equals J plus M trials. Then we can see the probability is just, behold, that. Probability that this coherent state is in that basis state. This is the probability of measuring a coherent state at theta phi to be in the basis state Jm. And it's the same as the probability of winning J plus M out of 2J trials, where the probability of winning a single trial is given by cosine squared theta over 2. In other words, when theta is 0, like we're at the North Pole, and the probability of winning is 100%. For coherent states at the North Pole, we're certain to win. When theta equals pi, the probability of winning is 0. So if our coherent state is at the South Pole, we're certain to lose. And at the equator, we have a 50-50 shot each time. And you're like, oh, what's special about the z-axis? Nothing. It's just that we've quantized along the z-axis. So our Jm states refer to the z-axis. Now you might wonder, where is all this expression with the sines and the cosines for the spin coherent state coming from? And I won't go into the full proof, but just to give you an idea of like how this can arise and sort of connect it to like the way that we talked about the spin coherent states before. So we can represent a rotation of omega degrees around an axis XYZ as an exponential, e to the negative I omega times x times sigma x plus y times sigma y plus z times sigma z. Now, if we have some unit vector pointed in the theta phi direction in spherical coordinates, we can express it in Cartesian coordinates, using this sort of sine cosine business. We can consider a rotation that takes the point at the North Pole to some given unit vector, specifically this vector, theta phi. And it's going to be this, e to the negative I theta times this times plus that. Now, if we define this complex number chi to be negative theta over 2 e to the negative I phi, remember theta and phi parameterize this point on the sphere, this can be written as e to the chi times the raising operator minus the conjugate of chi times the lowering operator.
Is the result chimerical? That's the actual origin of the word chimera
True,
in
true.
Greek, right? Is the result chimerical? Is it illusory?
Well,
Only
I
joking.
find that there's a lot, this is a kind of an interesting proof because of the way that you sort of, transmute between, using complex numbers and not using complex numbers, right? Like what's kind of, here, well, I guess you're using a complex number here, but, before when we parameterized our spin coherent states, we were using a complex number or infinity. But here we're using these two angles, right? We're kind of describing it in spherical coordinates as opposed to complex coordinates. So if it's chimerical, let's go with that. Now, again, the spin, to give an intuition, right, like about what the spin coherent state is, it's a state where like all of the stars, quote unquote, the stars are at the same location. Now we know that the, JJ state, right, like the highest weight state, is a state with all of the stars at the North Pole. So obviously we can get any spin coherent state we want by just like rotating the JJ state. So this is like ultimately what we're gonna do. We can parameterize the spin coherent states with just a rotation of the state where all the stars are at the North Pole, okay? So that makes sense, right? So, we can write the spin coherent state as like e to the chi whatever on JJ. So that's already pretty cool. And then you can do kind of a funny thing using the Baker-Cambro-Hausdorff formula. We can finagle this shit into the following form. This is a little hand wavy, but yeah, it works, where it's like an exponential of the raising operator, exponential involving the z operator, and exponential involving the lowering operator. And where instead of using chi, we're going to use this complex number z, which is just the stereographic projection from the South Pole of the point theta phi on the sphere to the plane. So then, you know, this here is just this rewritten. And then you observe like, well, you're like, oh, so this is just an exponential of the raising operator on JJ. But, you know, we know that's going to be like 0 for like all but the identity term here if you expand it out as an infinite series. So e to the negative, you know, conjugate of z times the fucking raising operator on JJ just gives you JJ. And further fiddling around allows you to rewrite this as just cosine theta over 2 to the 2j, which leaves you with that. And if you work that out, you know, playing around with infinite series and stuff, you can get this expression that we had before for the spin coherent state. So I just wanted to show you that, just, you know, how do, you know, because basically in this world of spin coherent states, you know, there's like 2 popular ways of like parameterizing it, right? Like you can parameterize it like this with theta and phi, you know, these spherical coordinates of somewhere on the sphere, or, you know, you can use these, you know, complex coordinatization where you use a complex number or infinity. And, you know, each has its benefits, right? I would say that this parameterization makes clear how, you know, intimately related this is to the binomial distribution. On the other hand, you know, working with the complex representation makes other things much more clear. Like, for example, we know that we can write, you know, a spin coherent state is just this.
You should,
Right?
if you're trying to get people to see it, you should probably put it on the screen.
Yeah, it's true. Oh yeah, let me do that. And in fact, it's reversed anyway, so it's like not even that helpful. As just a polynomial, f of z equals z minus alpha to the n, where n is the number of stars.
You just have to click on his picture and you'll see it.
Oh, okay.
In fact, I'll just write it out here real quick.
Okay, now I see.
F of z equals.
I'm happy to see that you're becoming Amish over time.
Yeah, exactly right. Just that, right? So alpha is like a complex number or infinity, again, you know, whatever, representing like the point on the sphere. And as I say, you know, the spin coherent state is just, you know, n stars in the same location on the sphere. And so you can just write the spin coherent state in this nice form, z minus alpha, where alpha describes the point on the sphere, to the n, where n is like the number of stars that you want. So like, you know, that's like an even more beautiful way of writing it. And in fact, this way explains like why you even have the binomial coefficient to begin with. Because, you know, when you FOIL this out or whatever, you know, like multiply it out, z minus a times z minus a times z minus a n times, you know, we know from Vieta's formulas that the relationship between the roots and the coefficient of a polynomial are just given by, you know, have to do with the, no, it's like less useful than I thought. Have to do with basically like the algebra of like multiplying this out. So, you know, what's kind of cool there is like you can see the binomial distribution arising simply from like the algebra of like multiplying out like these terms in this polynomial. We can also see that they like intimately relate to like the sphere and to the, you know, the actual binomial distribution from probability theory. Anyway, I just thought I'd say that. Just thought it was kind of cool. So, okay, but and actually the other reason I did this was just to, because we're about to talk about second quantized picture of spin. So I just wanted to like remind us a little bit about spin, because it's been a couple weeks since we really talked about some of the technical details of it. So, okay, so now we're actually gonna talk about second quantization, but like before I go on, are there any questions about anything we just talked about? Okay. So we have a one-dimensional quantum harmonic oscillator. Now we saw with our magical coherent state formalism, we can view it as like a constellation of forbidden classical oscillator states. Okay, but putting that to the side for now, we can view the harmonic oscillator, the quantum harmonic oscillator, as like a little guy that counts quanta. We can add quanta to it, we can subtract quanta to it, we can measure the number of quanta. It's like a little counting guy. The more quanta, the higher the energy, and the general state of the oscillator can be written as a superposition of different numbers of quanta. And what is a quantum? Here it's just like a little nugget of energy. It doesn't have an identity of its own. It's like the idea of a pebble, simple, indistinguishable. You add a quantum, what's the difference? You add another quantum, it's the same, it's like the same thing. Now, one of the simplest ways, again, this is just the simplest way, of understanding quantum field theory is via something called second quantization. And the basic idea is this. If you start with a quantum system living in some Hilbert space of dimension d, you can construct a theory of a variable number of indistinguishable copies of that quantum system by introducing a quantum harmonic oscillator for each basis state of the original quantum system. Hence, second quantization. In second quantized quantum mechanics, an oscillator is associated with each basis state of the original quantum system, and each oscillator counts the number of quote unquote particles in the state it's associated with. And because we use quantum harmonic oscillators to count them, the particles so described will always be as indistinguishable as the quanta in a harmonic oscillator. In the post for this week's meeting, I made this little meme, which I was surprised no one had made before. So maybe I should explain it. This is like a famous quote by some physicist, Ed Nelson. He says, "First quantization is a mystery, but second quantization is a functor." What is this, right? So functor is a category theory term. You know, the idea in category theory is to talk about categories. Categories have objects and categories have morphisms. In other words, transformations between objects. And a functor is a map between categories. It maps objects in the one category to objects in another category, and morphisms of the one category to morphisms of the other category. So in the first instance, we have, say, a first quantized quantum system. We could say the objects are states, and the morphisms are linear maps between states. We can then apply a functor, which maps states of the original quantum system to states of these oscillators, and linear maps on the original quantum system to linear maps on the oscillators in the second quantized picture.
Being a solipsist, I just thought a functor was a more fun version of Victor, but that's just, I'm sorry.
Nice. So, you know, for a bosonic field, you know, there can be any number of particles in the same state, and the particles are always in the permutation symmetric state. For a fermionic field, there can be at most one particle in a given state, and the particles are always in the permutation antisymmetric state. We're mainly going to talk about the bosonic case. Later on, we'll talk about the fermionic. And, you know, the punchline, you know, like as I'm sure you're all basically aware, is that our current theories of physics, you know, regard all so-called particles as quanta of some quantum field, as indistinguishable, like countable nuggets. You know, it's like An electron doesn't have a beauty mark. All the electrons are basically the same. Now, when you actually talk about quantum field theory, you can think about, you know, a quantum field as just the first quantization of a classical field. But then there's this other perspective that you can view it as the second quantization of just the ordinary Hilbert space of a single particle. We're not going to go into the details of like field quantization here. We're just going to like talk about this at a very high level. But the simplest example of a quantum field, I would say, involves second quantizing a spin half particle. The system has two states, up and down, and so we're going to introduce two quantum harmonic oscillators. We could say the first oscillator keeps track of the number of up quanta, and the second oscillator keeps track of the number of down quanta. By construction, we'll get a theory of a variable number of permutation symmetric spin half states. But we know what a permutation symmetric state of spin halves is. It's a spin J particle. We talked about that already. And so we can look at our double oscillator construction as a model of spin with variable J. In other words, where the J value can change. And we're gonna have a superposition of different J values. And in some ways, this is what we've been building up to for so many months, right? I've tried to use spin as like the paradigmatic case of a quantum system. And at each step of the way, we've seen kind of like different mathematical representations of it, right? We were able to represent spin as a JM state. We were able to represent spin as a complex polynomial. We were able to represent spin, you know, in terms of these coherent states. We were able to represent spin as, you know, a permutation symmetric state of 2J spin half particles. We were able to represent it as, you know, in terms of a polynomial in two complex variables, and we'll actually see how that idea recurs here. And now finally, we're gonna see how it all comes together in this oscillator representation of spin.
Matt, can I ask you a question? I don't know if I'm jumping the gun, but putting spin aside, you know, the Fourier components are creation and annihilation operators. Is that the same thing here? You know, where
Yeah.
spin up is would be analogous to a creation and spin down an annihilation operator?
Exactly, yes.
So, so you could use one to you could change a particle from up to down using a creation or an annihilation operator. It would be the same math as in creation and annihilation of particles.
Yeah, exactly. That's what we're about to see that. Yeah. Exactly.
Oh, okay.
Exactly right. So we could write this. So I'm going to write this out in like the occupation basis notation. But like, let's use polynomials first. So suppose we have like one oscillator state, which is like some polynomial f of z. I've suppressed the coefficients. I've just written out the powers of z. Okay. And then here's like another oscillator state. It's polynomial in w. And again, I've suppressed the coefficients. So you imagine there's some complex numbers weighting these. Each one of these represents, you know, a state with n quanta. So, you know, if we tensor these together, that just amounts to like multiplying them. And, you know, so you get this polynomial in z and w, and, you know, here's like z to the 0 times w to the 0, z to the 0 times w to the 1, z to the 0 times w squared, z to the 0 times w third, et cetera, et cetera, et cetera. Like these are all the, you know, w terms multiplied by z to the 0. And then here's all the w terms multiplied by z to the 1. Here's all the w terms multiplied by z to the third, et cetera, et cetera. It's just some infinite degree two variable polynomial. But obviously, we can like rearrange this as a sum of homogeneous polynomials. Remember, a homogeneous polynomial is one where each term is of a fixed degree. So here's all the terms where of degree 0. It's just z to the 0 times w to the 0. Here's all the terms of degree 1. You got z to the 1 times w to the 0 plus z to the 0 times w1. Here's all the terms of degree 2. Here's all the terms of degree 3. Now, if you remember, like way back when, we already talked about exactly this idea. When we were talking about representing spin in terms of homogeneous polynomials. Let me go back to it. Here. You know, we could either represent, say, like a qubit as a single variable polynomial, or we could homogenize it by adding this extra variable w. And we were able to, you know, do this whole thing. So, you know, to remember that, like, go check out this, these notes. So, where'd it go? Beep, 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 beep. So, you know, we can regard a two-variable polynomial as just a sum of homogeneous polynomials of 0, 1, 2, 3, 4 degree. Each such sector of the Hilbert space corresponding to a given total n, where n is like the degree, can be interpreted as a spin n over 2 state, where n is just 2j, the number of stars. So concretely, we can write this correspondence between, you know, the occupation number basis of 2 oscillators, the spin basis in the JM representation, and the states of 2J symmetrized spin halves, which is just this. So here to the left, we have the states of the oscillator, you know, recall it, you know, this in this notation, you know, 0, 1, 2, etc. That's like the number of quanta in the oscillator, and there's 2 of them. So we have 2. So this is like, there's 0 quanta in each of the oscillators. This corresponds to the JM state 0, 0, you know, J is 0, M is 0, and just like some bullshit 0 state, whatever, spin 0, not that interesting. Can look at the state of total number 1 of the 2 oscillators. So
Spin 0 is not a bullshit state, it's the Higgs, my friend.
Well, I'm just trying to think of like how to notate that.
The Higgs, I just want to let you know, the Higgs is presiding over this entire discussion, okay?
Yeah.
Just remember that.
Yeah, fair enough. So, you know, we can write the states with like total 1 quanta of the 2 oscillators. It's just these. There's these 2 possible ones. 1 quantum in the one oscillator and none in the other. No quanta in the first oscillator, 1 in the other. And these correspond to, you know, spin half up and spin half down, etc. If we look here, you know, these are states of total number 2 of the 2 oscillators. So what are the possible states? Okay, 2 in the first oscillator, none in the second. Then you could have like 1 in each oscillator, and then you can have none in the first and 2 in the second. And these 3 states correspond to the states of a spin 1 particle. Here's, you know, the spin up state, spin 0 state, spin down state. And then in terms of the symmetrized spin halves, you have up, 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 down, plus down, up, and down, down. And you see like the connection here, right? This 1, 1 state, right? It says, okay, you know, there's 1 up and 1 down. And, you know, because we're using like oscillators, this is supposed to somehow correspond to like permutation symmetric states of spin half. We see here, this is the state form where it's just like, okay, there's 1 up and 1 down, but like we don't know which one's which because it's permutation symmetric. So up, down, plus down, up. Similarly here, we're saying, all right, in the up oscillator, we got 3 quanta and none in the down oscillator. And that corresponds to the highest state of spin 3 halves particle. And in terms of our symmetrized spin halves, up, up, up. Then we could have, you know, 2 in the first oscillator and 1 in the second oscillator, you know. And we see here, like these are the sum of the states where there's 2 ups and 1 down. Over here, these are the sum of all the states where there's 1 up and 2 down, and so on and so forth. And so you can see that actually, you know, one of the simplest examples of second quantization is just the theory of spin. and it has to do with how you build the spin J representations out of the fundamental spin half representation. So now to have like a functor, right? Functor's got to map, states to states and, objects to objects and morphisms to morphisms. So in a way, here's how we can map, states to states. These are like the objects. But what about the linear maps? What about the morphism? How do we upgrade a morphism, a linear transformation that acts on, say, a spin half to one that acts on the two oscillators? And it's quite easy. We can upgrade any 2x2 operator on the spin half Hilbert space to act globally on the Hilbert space of the two oscillators via this simple map. In other words, we just basically like form a little bracket where A, B, and C, those are just scalars, right? This is just like some 2x2 matrix that acts on the spin half. And we're multiplying it by a bra and a ket. But where, remember, A0 and A1 here, these are the creation and annihilation operators of the two oscillators. Those are matrices. So, you can work it out. Here's Pauli X, Pauli Y, Pauli Z. And, you just multiply it out. And it turns out that the, spin matrices have these simple representations in terms of creation and annihilation operators. If we upgrade, the X operator, it'll act as an X operator on each of the spin J subspaces. We exponentiate it and use it to rotate. Oh, it'll rotate all of the subspaces at the same time.
Somebody was just trying to speak, but I couldn't hear what they were saying.
Oh, well, Moshe just, now we have two views of Moshe. Two simultaneous pictures. Now, here's the connection to what you were asking about, Michael. Or actually, Moshe, I'm getting a little bit of an echo from you. Whoops. So, Michael pointed out that, like, when you normally think about field quantization, you're decomposing the field into these Fourier coefficients, and then you associate each one of those coefficients with a creation or annihilation operator. And, that's exactly what we're going to do here. But, we're not dealing with the Fourier coefficients of, a field. We're just dealing with the complex coefficients of a little spinner, of a spin half.
Finally, some metaphysics, creation and annihilation. Okay, I'm all in.
Yeah. So if you have some spin half state, alpha beta, you can form a star creation operator that's just, alpha times the spin up creation operator plus beta times the spin down creation operator. And this will, basically raise the J value, right? If you start off, if you're in the vacuum state and you just have a spin zero state, basically, if you act with this star creation operator, it's gonna like pop you up to a spin half state, and the spin half state's gonna have a star at the location corresponding to alpha beta. And then you can, add another star, or, whatever, pop it up to a spin one representation and so forth. Now, we know that we can decompose a spin J state into 2J spinners. We know we can decompose it, as we would say, like into 2J stars, right? We can represent those stars in terms of spherical coordinates or complex coordinates, or we could use spinners or whatever. And then we could obviously lift the constellation into the double harmonic oscillator Hilbert space, like one star at a time, like using this thing, right? But why would we do it one at a time? Why not do it all at once? So we could associate a homogeneous polynomial in the creation operators with a constellation and raise a constellation out of the vacuum all at once. And so you see, it's just this. And this is just like literally like outside of that, there's outside of the missing powers of -1 here. This is just the same thing as the Majorana polynomial in its homogeneous form, where instead of having complex variables z and w, instead we have these powers of the creation operators. So if we have some like JM state with these complex components, we can just form a, turn it into a polynomial in the creation operators. And when we act with this operator, it'll create a whole constellation. In other words, if you start in the spin 0 state and you had, say, like a spin 1 state, it's got 2 stars, you plug the coefficients into this expression, and it's like, boom, it's just gonna pop you up to a spin 1 state, and the stars are gonna be in the appropriate location. And, in fact, this formulation of spin, the oscillator representation is also known as like the Schwinger representation, after like Julius Schwinger, famous Harvard professor, who have been given to understand, like when he was like 18 or whatever, in like the 30s or 40s, he like read Majorana's paper and he was like, WTF, like how can this work? Like how can you just represent a spin state with like a polynomial and the roots, and like what the fuck are you talking about? How can it be? And he spent time thinking about it, and then eventually invented oscillator formulation in order to understand it better.
But
Now,
here,
I have a cool
here WTF is what the fuck.
What the Fox space.
What the fuck, yeah.
Yeah. So I have a cool visualization of this double oscillator formulation. But before we do that, actually, because there's I should explain one more thing, just because it's part of the visualization. And that is the connection to polarization. So we're talking about polarization before. So here's the punchline of that, right? So we can represent spin with 2 harmonic oscillators. Cool. But like, what's the meaning of like, say, the position operators of those individual oscillators? Like, and we can just view them as like abstractly counting the number of up quanta versus like the number of down quanta or whatever. But, we could also think about this as like a 2-dimensional harmonic oscillator. We're imagining that like, the 2 oscillators are, the positions are at right angles. And so this is like a little 2-dimensional oscillator in the plane. And it turns out that like this actually is a very useful thing to do. Because if we look at, say, the amplitudes for the position of this 2-dimensional oscillator on the plane, and we examine, what's going on with the eigenstates of like the XYZ operators, one finds that they correspond to like diagonal and like anti-diagonal oriented states for X, circularly symmetrical states for Y, and vertically and horizontally oriented states for Z. And this should immediately make us think of the polarization of light. So, classically, light waves rushing towards you, right? It's always got to move like at the speed of light in its like direction of motion. Like that's, never in doubt. But, it's free to like oscillate in the plane orthogonal to its motion. And so, famously, this gives light a corkscrew character. And, that's called its polarization. And, you can send light, as we've been talking about, through a polarizing filter. You can filter out the horizontally polarized light, whatever. So it turns out like another way of interpreting our construction is as a model for the polarization of light, oscillating in the 2D plane orthogonal to its motion. And actually like this and its connection to the sphere was already known even before quantum mechanics in the 19th century. Look up the famous Poincare sphere. If we imagine a classical picture of the polarization of light, what can we generally make, right? It's like you could have horizontally polarized light, you could have vertically polarized light, but you could have some combination of like horizontal and vertical, and that's gonna make like an ellipse. But you know, like what's an ellipse? But like a circle seen
We're
askew
losing you.
in 3D.
We're losing you
Oh,
completely.
hello? So,
Can't hear you. Way in the background.
okay, can you hear me now?
No, you're like at about 1/10 the decibel level.
Okay.
I can hear you perfectly well, Matthew. Nothing seems to have
Okay,
changed.
so maybe it's my connection.
Is Moshe, are you still there?
Clunk.
By the way, Matt, is this taken from Penrose's book,
Yeah, this image is taken from Penrose, yeah.
Road to Reality? Yeah, looks familiar.
I love that book. I love that book because it's like, you know, I've had it for like a decade now. And it's like, it allows me to track how much I've learned. Because like when I first got the book, I understood like none of it, you know? And then like a year later, I was like, okay, I understand like 3 chapters of this. And then the next year I was like, okay, you know, okay, like maybe 5 chapters, like maybe it's pushing it. It's like
Can I ask a
feel like
question?
I get a little bit, what?
Can I ask regarding polarization, your opinion? You know, in the classical sense, field polarization, you know, I guess on a macroscopic scale, we can look at it as a corkscrew type of phenomenon. I guess that can be shown. But how do we interpret that for, let's say, a single electron or a beam of electrons? You know, that is just one. I don't mean an electron, a photon. A beam of photons that's only 1 photon thick. Can we envision that as a corkscrew? Because then we're back to envisioning spin as the thing actually spinning.
Well, in a way you can. So, I mean, you can, as he says here, right? You can represent like photon polarization states using the Riemann sphere, like using.
Well, yeah, but this is a mathematical representation. I'm saying physically, how do we envision polarization? Is it actually the spinning of the electromagnetic field macroscopically?
Well, let me show you like these next 2 things, and then
Yeah.
I'll answer your question. So, you know, here's one way of like, suppose you're given like a qubit or whatever that's supposed to represent the polarization degree of freedom of a photon. You know, one way of deriving its like ellipse is like this. If you imagine that like this is the direction of the photon's motion, of its momentum, and you identify that with like the y-axis of the sphere, then if you take like a general polarization state can be written as some like W plus, you know, left-handed circularly polarized plus Z times, you know, whatever, counterclockwise, circularly polarized, right? So you can represent it as a superposition of clockwise and counterclockwise. You take the ratio of the 2 components and then square root it. And that gives you this point on the sphere. And then what Penrose tells you to do is, he's like, all right, imagine the plane at the equator, cutting here. Then take that little point on the sphere, drop a perpendicular, and you get this plane. And then you drop this plane onto the equator. And that makes this shape. And that shape could be like a line, it could be a circle, it could be an ellipse. It's like, that's the polarization ellipse. Now, there's another way of thinking about it, which is like more calculationally, like that's a very geometrical thing. This is like a more calculational thing. If you just take a spinner, okay, and rotate its overall phase while taking the real parts of its 2 components to be X, Y, Z points on the plane, that's going to draw out the appropriate ellipse. And you can think about the meaning of the XYZ operators as being like 3 different ways of drawing an ellipse on the plane using oscillatory motion. In other words, you could draw an ellipse by adding together oscillatory movement horizontally and vertically, each starting at some phase relative to each other. You could also use, obviously, oscillatory movement at 45 degrees from that, diagonal and anti-diagonal phased oscillations. Or you could add together left-handed and right-handed circular oscillatory motion. And each of these different ways of moving can equally well draw out an ellipse in the plane. So actually this gives us like a totally other way of interpreting the geometry of a spinner. So you can think about like a spinner as representing like the classical spin of a massive particle. There, it represents both the axis of its rotation and its phase represents like how much is like rotated around the axis. Or you could interpret it as like describing the polarization of like light, photon, like a massless particle, where the spinner represents both which ellipse you're talking about and also the phase. So we can visualize it. So here, what I do is, let's see if it runs. Okay, so what I do is I generate like a random spinner, and you know, it's just 2 complex numbers. Here is it represented as like a point on the sphere. You know, I just take the expectation values of X, Y, and Z, and I get this axis, right? But then what I can do is rotate its overall phase in time. And as I do so, take a look at just the real parts of the 2 components of the spinner. And you see that they draw out this ellipse on the plane. So like, let's look at our basis states, right? So let's look at spin Z. Spin up just corresponds to horizontal polarization. Let's take a look at spin down. You'll never guess. It's just vertical polarization. Let's take a look at you know, X plus over here. It gives you diagonally polarized. If we look at the X minus state, it gives you diagonally polarized in the opposite direction there. And finally, let's look at our Z states, our Y states. You're following along, you know, this should correspond to, you know, this is right-handed, circularly polarized. And let's look at Y minus. It's going to be circularly polarized in the opposite direction. So again, this is why we love spinners, because they can simultaneously represent the state of a classical spin, a rotation axis, and an amount that you're rotated around that axis. And also a classical state of polarization, where you get both a particular ellipse and an amount that you rotate around that ellipse. And then the exact same mathematical structure can be interpreted like directly as describing the quantum state of the spin of a spin half particle, say a massive particle, or as the polarization of a massless particle, but where you just have to realize that you can't just directly like look at the polarization or the spin, but you got to use your X, Y, Z operators and like measure it. And so, you know, the spinner shit is beautiful for just that reason. So, you know, don't let anyone tell you spinners are confusing. They're not confusing, they're just awesome. You know what I'm saying? They're just like polysemous. They just like simultaneously like are able to represent like a lot of cool shit. Love the spinner thing. That's why Penrose loves them. Okay, so, you know, we have a model for the polarization state of a photon, ignoring its momentum. All right, so then if we consider our double oscillator construction, we can view this as like the polarization state of like potentially several photons, just like all in the same momentum state. Each photon has like a qubit representing its polarization state, and the photons are bosonic fields, so all the qubits are in the permutation symmetric state. Technically, a photon is a spin 1 particle, but because it's massless, there's only 2 states that are relevant, and so you can consider it like a qubit. And, you know, this is just, again, this whole spinner thing, like, I just want to emphasize this continual, like, duality between, like, the plane and the sphere. The plane and the sphere, right? Like, complex number on the plane, stereographically project to the sphere. Sphere is, like, rotating around an axis. Plane has, like, polarization. The same state can represent the polarization of a massless particle oscillating in a plane because it's moving at the speed of light, and also the spin of a massive particle, where you got to consider. So, you like in my head when I think about it like, imagine a particle like, you know, moving at the speed of light. Like it can only oscillate, you know, in this plane orthogonal to its motion. But like, imagine like it were slowly able to gain mass. It would be like that plane like wrapped itself around a sphere, and then its polarization would just be its spin. In other words, like this is the duality between spin and polarization. They're the same thing. It's just polarization's for massive particles, sorry, massless particles, and spin is for massive particles.
But can I just, you know, getting back to my original question,
Mm-hmm.
relating this, I mean, I don't know if you have an opinion on this, but relating this to the macroscopic world, if we look at a ray of light that's polarized, do we actually, is it actually the field, the macroscopic field that is spinning around an axis? Or does this only apply at the, you know, at the quantum level? I don't know if you have an opinion on this.
Well, I mean, I think that it's, I mean, you know, insofar as there's, you know, this quantum to classical correspondence, it's like, yeah, you know, I mean, at a certain point, yeah.
So is the macroscopic field actually spinning? Is it actually a corkscrew? I should know the answer to this, but I don't.
My understanding is, yeah, I think that's a perfectly valid way of looking at it.
Yeah. Can I ask a personal question? Did you grow up? Have you ever lived in Baltimore, or is either of you? What?
No, but you know, I grew up, you know, in South Jersey /
Is either of your parents from Baltimore?
No, do you think I talk like I'm from Baltimore?
Well, I heard you on several occasions add an L to the word draw. You said drawl, and that is a typical Baltimorean speak.
Well, South Jersey, it's not that far away, so there might be a little bit of.
Is it also? I mean, is it also
drift.
South Jersey and Philly? I had a girlfriend who was from Baltimore, and she would always add an L after the W. You know.
I mean, I definitely have a South Jersey-ish accent.
Because I know people from South Jersey, but I've never heard that particular pattern.
Like, there's a very distinctive, like, Philly accent, which, like, I don't have, like, that much. But, like, for example, I will say, like, water as opposed to water.
So none of your relatives are from Baltimore?
No.
Because adding that L is really, it's characteristic of a Baltimorean speech pattern.
My father said Earl and Turlet.
Well, that's
Lower
New
East
York.
Side. Lower
That's
East
New
Side.
York.
Earl and Turlet.
Was your father Art Carney? Was your father Ed Norton?
He cracked me up every time he said it.
So, you know, one consequence of this kind of beautiful duality between polarization and spin, you know, is like we can build a quantum computer out of spins, or we could build a quantum computer out of like light. And as we've just shown, we can easily translate between the two. We can represent spin operators on the, you know, on the polarization of light. We can represent, you know, these photonic operators on spins. They can simulate each other. But, you know, of course, I emphasize that this is more profound than a classical simulation. Because if I load in a given quantum state into my quantum computer, made of spins, made of light, whatever, this in principle won't affect its entanglement to other systems, like outside the computer. And so, you know, we're dealing with something more than simply a representation, like with digital computers, where it's just all zeros and ones. It's more fundamental.
What if the quantum computers begin to, you know, unwittingly rewrite the rules of the quantum world?
Well, then I, I hope to see the day, you know, I'd love to see it. So let's take a look at this. So here we go. All right. Now, how the frick does this work again? Sorry. Just got to remember what the keys are. Okay. So, you know, what are we looking at here? First of all, I choose a random spin 3/2 state, just for sake of argument. And it's this little red guy here. Then I load it in to my two oscillators using that constellation creation operator. And this is that guy. So you see already, like, these two constellations are the same. In the middle, you see, like, this is like the polarization plane. And each one of those arrows, like, represents like the amplitude at that position. And the whole thing's evolving under the oscillator Hamiltonian, and so they're just all spinning around. And you got the yellow dot there represents the expected position. So for example, I press I here, we can just generate a random state. And so what I've done is I've decomposed, you know, like I've been saying, the Hilbert space of the two oscillators into, here's the spin 0 part, here's the spin 1/2 part, here's the spin 1 part, here's the spin 3/2 part, here's the spin 2 part, spin 5/2, et cetera, et cetera, et cetera. And, you know, the general state is like a superposition of them. And so I represent like the probability of like that sector with the opacity. So then I can, what do I want to see now? All right, so for example, let's choose as a Hamiltonian, like one of the Pauli operators. So I take, say, so when I press S, it just chooses like Pauli X, Y, or Z at random, and then like upgrades it to act on the field. And you can see what it does is it just rotates each of the spin sectors around. You know, now we're doing a Z rotation. And so, you know, this is like the functorial thing, right? I could take like the Z operator. It's just this like 2x2 matrix that acts on the spin 1/2 state. And then I upgrade it into an operator that acts on like this quote unquote field or whatever. And you see it just rotates all of these guys, you know, individually. Now we're doing a X rotation. Okay, that's cool. That's cool. We can choose, you know, just some random Hamiltonian. And you see, you know, in general, the constellations evolve somewhat arbitrarily, and, you know, there are different probabilities evolve. Okay, let's go back to the oscillator Hamiltonian. What do I want to do? Okay, so like, for example, okay, so we could measure like the number operator. So boom, when you measure the number operator, it like collapses to being a spin J, particular spin J particle, right? So you measure the total number operator, it collapses to like one of these subspaces with a certain probability. Now what happens if we measure the X, Y, or Z operators? We can see this correspondence like I was talking about before. So I've measured, like, say, the X operator. And you see, I don't know if you can see, like, these arrows here are kind of oriented diagonally. I'll choose a random state again. Here's another X eigenstate. Here's another X eigenstate. This one's diagonal in the opposite direction. Here's another X eigenstate. Okay, it's a little less clear. Okay, that one's clear. That's definitely diagonal. Okay, so these are what the X eigenstates look like. Let's check out the Z eigenstates. Oh, look at that. So vertical. Here's another one. Oh, horizontal. There it is. Z eigenstates are like horizontally and vertically oriented. What about Y? Boom, look at that. It's so circular. Again, circular. So there you go. There's the correspondence. When you think about X, Y, and Z operators, you're talking about, you know, X, Y, Z axis of a massive particle and its spin. Talk about massless particles. You're talking about diagonal versus anti-diagonal versus horizontal, vertical polarization. Just for fun, like, we can measure the position. Bing, oh, it collapses there. And you see that like a state of definite position in this plane, you know, corresponds to like a superposition over all J values. Kind of interesting. Start over, random state, measure the position again. Boom. Again, superposition over all J. So that's kind of interesting, right? Like, to be in a state of definite position in this plane, you know, that the photon's oscillating in, is to be in a superposition of different, like, numbers of photons, or interpret as spin, like different spin J representations. So how about that? Pretty frickin' cool. Now, one, you know, thing I should note is that, you know, for this correspondence to like really be exact, we'd have to be working with, you know, infinite degree polynomials, right? But what I've done is I've like truncated the oscillators to have like a certain maximum number of excitations. And so what that means is you can actually see that this sort of spectrum of different J values is symmetrical, right? This kind of looks like a spin zero state over here and a spin zero state over here, a spin half state over here and a spin half state over here. That's just a feature of the fact that we've like truncated the number of excitations in our oscillators. In general, that would not be the case. So does that make sense? Is it clear what's going on in this sort of simulation here? Let me know.
So tell us, Moshe, as a PhD in professional physicist, have you understood every single part and particle of this presentation? Yeah. Moshe, where are you, Moshe?
Oh, Moshe. You know, we can look at kind of the code.
Moshe has turned into like a deist god. He's just God paring his nails.
Where was it? Oh, here we go.
Matthew?
Yes.
to go to Victor's point, there's an awful lot here that you, again, and it just becomes difficult to absorb it all at one time.
Yeah. Okay.
So
Sure,
we've been going for 2 hours now. I think you might, if this is a good place to break, I think that would be good because.
Sure. Well, let me just get
As
through
I
this.
pointed out, there's an awful lot I have understood.
Let me just get through this next section because it's quite short, and then that was where I was going to stop anyway. So, what we've seen is that we can start with a spin half state, which is 2-dimensional. And we can obtain all of the spin J representations through this kind of functorial construction, where we associate an oscillator, quantum harmonic oscillator, with each of the basis states of the spin half. In this case, there's 2 of them. And so we get 2 harmonic oscillators. We can take any state of a spin half particle and upgrade it into the Hilbert space of the 2 oscillators. We can take any operator that acts on the spin half particle and upgrade it into an operator that acts on the oscillators. And in this way, we can, in one go, get all of the spin J representations, and in fact, represent superpositions over those spin J representations. Now you might wonder, can we do this in general, right? And we can, and it's basically, this is like the idea of second quantization. So for example, suppose we were interested not in SU2, rotations, little spin half particle, but what about SU3, having to do with the quarks and the gluons and that, right? That acts on like 3-dimensional complex states. We could do the same thing, but we'd need 3 harmonic oscillators. And actually we'd need 6, because SU3 is rank 2. And I won't go into the details, but that same thing works for any SUN. And in general, we can construct theories of a variable number of indistinguishable particles with different symmetries. The oscillator space can be interpreted as a superposition of these higher order representations. And in a second quantized context, and this is sort of like the philosophical point I want to make, we can regard like any measurement as the measurement of like the number of particles in a certain state. So like we can rephrase like a spin measurement like along the z-axis in terms of like counting the number of quanta in an up oscillator or counting the number of quanta in a down oscillator. We could like rotate those creation annihilation operators so we could try to get, number operators that count the number of, horizontal or horizontal in the other direction quanta. And so once we sort of second quantize, we can think about any measurement in some sense. And I don't know, maybe this is like a little bit, I don't know if this is exactly true, but it feels true. We can think about any measurement as in some sense being reducible to the measurement of some number operator. So in a way, we've come full circle. We can now contextualize our pebbles as counting the number of indistinguishable quanta of some mode of a quantum field. And so what I want to end with is, and I hope Michael's still here, just a simple example of a quantum field theory where we're actually, talking about position and stuff. So I'll just boot that up and then we'll head out.
Here's how I wanted to end. And please, I'm going to start with a line that sounds like I'm disparaging, and it's the very, very opposite.
Okay.
You're like an idiot savant with leaning on the savant in that coupling. You're like an idiot savant who is playing 3-dimensional or n-dimensional spin chess.
I love spin. It's true.
So
I literally dream about it. Like literally last night, I like woke up and I realized I just was like having some dream that was like entirely like in math. And it was like about like that binomial thing I was showing you guys before. Messes with your head, I'm telling you. Yes, I do take it as a compliment, thank you. So what I've done here is, okay, so like last time we talked about the harmonic oscillator and its coherent states. And the coherent states were like classical, like little Gaussian wave packets that would just like oscillate around or whatever. So now what I've done here is I've second quantized the harmonic oscillator. In other words, like the harmonic oscillator, you had like a certain probability of being a different position or whatever. Now there's a harmonic oscillator for each basis state of the original harmonic oscillator. And I've also added a spin to each location. I then, I have the oscillator Hamiltonian that acts on like the Hilbert space of just the oscillator. Just like in the previous example where I could like take the Pauli X operator and like upgrade it to act on the oscillators, I could also take like in this case, the harmonic oscillator Hamiltonian and have it upgraded to act on the field. And so now what this is you're seeing these cylinders represent the expected number of particles at that location. So I upgrade the oscillator Hamiltonian and I upgrade an oscillator coherent state. And you see that the expected number of particles is now oscillating exactly in the same way as a coherent state of just a single oscillator. So like, whereas before the oscillation was like, what's the probability of finding this oscillator at a certain location? Now it's like, what's the expected number of like second quantized oscillator particles that we expect to find at that location? In other words, we've taken our construction before, but now we're imagining that there's just like some variable number of them. Furthermore, I've added like a spin. And so you can see here, like, what is the expected spin in each of the locations? So I just, add in a random spin value to start with. And so you can see, like, as this guy oscillates around, the expected value of the spin kind of tracks it. And, if I hadn't added the spin, then say, if there were 1, 2, 3, 4, 5, 6 possible positions, then I would need 6 harmonic oscillators to keep track of the particles like in each of those positions. But actually I need 12 because I also want to put a spin in each location. And so at each location, I need an oscillator for up and an oscillator for down. So in total, I need 12 harmonic oscillators for this construction to work. So it's, it's just a bunch of oscillators, basically. So this is just a very, very simple toy example of a quantum field theory. Next time, maybe we should give it a rest here. But next time, I can go a little bit more into the details of this. But I mean, if you just sort of look at the code here, I can, maybe we'll save that. Essentially what we're doing is just exactly the same as this. But see, in the spin case, we start with 2 by 2 operators, and we have 2 harmonic oscillators. In the case I just showed you, these operators would be like 12 by 12. And there would be 12 creation operators and 12 annihilation operators. So all we've just changed really is like the number of oscillators. And like I say, we can take any state of the single particle the single particle Hilbert space and any linear operator that acts on that single particle Hilbert space and apply this functor, right? That takes a state of the single particle Hilbert space and gives you a state in the second quantized space of some number of indistinguishable copies of that original Hilbert space. We could take any linear operator on that original Hilbert space and upgrade it to an operator that acts on the field. And so that's in the sense in which first quantization is a mystery, second quantization is a functor.
Here's your assignment for the next. I'm about to leave so I can see LeBron James.
Oh,
So
very nice.
your assignment is to calculate the total angular momentum, orbital and axial, of all the electrons in the basketball when LeBron James, hits a three. Okay, that's your.
Well, you're so right that, yeah, it seems like a lot of the magic of basketball and a lot of these games involving balls is kind of like, adding some kind of weird like torque to it. So that like, it's not just like spinning, but also kind of like precessing like around its spin axis. So then it kind of like moves in a kind of unpredictable way. It's a good point. It's a good point.
I'd rather give you a different assignment, Matthew, which next time, if you could summarize what you think you've done in a way that addresses directly to the intuition of the formalism. So I think that every time we come back to this, it's hard, for me anyway, to remember all the intricacies. And therefore, it just would be helpful if you try to intuitively summarize where we are up to there. So when we go forward each time, we're bringing forward our understanding that you brought from last time.
Sure, yeah, I definitely will. Well, Andre, like, did this part make sense to you here? This sort of correspondence between...
Yes, it did. Yes, it's quite beautiful. And you did it twice, I think, actually. And I'm just saying, next time, you have to do it again, which is go through the intuitive statement of each of those columns. Gotcha. What does the first one mean? What does the second one mean? What does the third one mean? And that will orient us to go forward, I feel. That, as I said, you said it twice, but how much we're all going to remember for next time, that's why you got to keep repeating it.
Okay, yeah, definitely. Yeah, I'll go over this again. And I'll also, I'll work out a couple, like in a more elementary way, some of these calculations, just to make
Give me some recursive structure.
Yes.
Give me some Hofstadter. Give me some recursive structure here.
Yeah. No, I mean, I think recursion is exactly what's happening here. It's like each level is sort of, building atop the previous level, and the pattern is always repeating. Yes. Yeah. Thank you for the feedback. I think one random limitation, this isn't quite an excuse, but it's like it's great to have like the Python code here in the notebook, right? Like here, you can kind of get kind of like intuitively like what this is doing. Like this is the one that draws out the polarization ellipse. It's just sort of like, all right, you're just taking the real part of the vector and showing it. And at each time step, you're multiplying it by like a little phase. But then some of these more complicated simulations, I end up putting, they're quite long, so it doesn't make much sense to put them in the Jupyter notebook. And so then, what the code's doing is like a little bit abstract because you can't see it directly in front of you.
That's right, Michael. Matthew. So what you're saying is the way that is listening to you, is reading you, is doing the calculations, is reading the code, and then there's creating the code. Yeah. Each level creates a different level of intuition for what's going on.
Totally, yeah. So I'll work out in the notebook some like step by step. Here's exactly the calculations we're doing to get from spin half through the oscillators to the oscillator representation and stuff. It'll be good. And then after that, in the next section, you know, it'll be fun. We'll talk about some other uses of these oscillators, to talk about a little bit about curved space-time. I'll talk a little bit about the 3-qubit code as a model of holography. Just a little heads up about what's to come. So, you know, stay tuned for that. Yeah, you know, if there's no other questions or concerns, you know, thanks again, as always, for showing up and listening.
Thank you very much, Matthew. I'm going to dinner. I'm going to dinner.
Oh yeah, I gotta do that too. See ya.
See you next time.
How do I get out of this thing? And, yeah.